Yes, questions?
What's your answer?
I won't give an answer to that one. If you still remember that question at the end of the semester, after the finals, just pay a visit to me. Any other questions? Let's do another example. Now this time let's imagine we have parallel plates and we put some charge on our plates. We apply a potential difference and we create a uniform electric field inside. And when we take these parallel plates and put it in a region of space where there is a uniform magnetic field into the screen, so we have an electric field pointing downward, magnetic field into the screen. Now let's imagine we send a charge through it with a velocity v. We have a charge q, we just send it with a velocity v in that direction. What is the direction of the electric field acting on this, assuming q is positive? Let's say this is the y direction. The electric force acting on this is electric field upward or downward? Electric force, not magnetic force. Well, it's just q times E. If q is positive, it's just E. It's downward. It's q times E in the minus j hat direction. Remember, the total force acting on this is there is an electric force and there is also a magnetic force. So there is a part which is due to the electric field plus another part of the the force due to the magnetic field. Now, this is the force due to the electric field. What about the force due to the magnetic field? What is the direction of that force? Let me see your right hands. V, four fingers in the direction of V, palm in the direction of the magnetic field, thumb is pointing upward. So that is the direction of the magnetic field. So if you just sum them, you get the total force. It is Q times E minus, VB minus E. You see, E is fixed, B is fixed. If you prepare the setup, you choose some particular E, some particular B. But when you send some particles through the system, usually those particles will have different speeds. And there's if the speed of the particle is such that V is equal to E over B, if V is equal to E over B, the force will be 0. So if the speed of the object that you send is faster than E over B, in which direction will it accelerate? If the speed of the object is larger than E over B. If V is larger than E over B, this will be positive, so it will accelerate upward. So it will go upward if V is larger than E over B. Because in that case, the magnetic field will be stronger, magnetic force will be stronger than the electric force, so the particle will just bend upward. If the speed of the object is less than E over B, in which direction will it bend? If it is slower than E over B, well, in that case, the magnetic force will be small, the electric force will be larger, so it will just bend downward. Only if the speed is equal to E over B, it will just go straight. So essentially, if you put suppose you put some very narrow hole over here, where you send your particles, and on the other end you put another hole aligned with the initial hole. You send your particles through this hole, so only those ones that go straight will be able to pass through the other hole. And the ones that go straight have the speeds E over B. So if you need to find some particles that have a definite speed, well, this is your speed selector. So for example, one treatment of materials is, one way of treating the materials will be just to send some electrons and just bombard your material with electrons. It changes the chemical properties of the material. And one way of, at least if you want to study how the electrons change the properties, what you would like to do is you would like to create some electrons with a particular properties, like a definite energy, so that by adjusting the energy, you can obtain different effects on the material. Their strength even changes. So this is one way of choosing electrons that have a definite energy. And in fact, this kind of led to the discovery of the electrons also. Now, in the case of the discovery of the electron, what we had actually done was we had a hollow tube. So you have a cathode, and then you have an anode. No, not the anode is not over here. The anode is over here. We applied a very large potential difference. So here there is you have the electrons, and here it's essentially a grid. So you have the negative potential over here, you have the positive potential over there. If this potential was strong enough, what we observed was that there is a glow over here. So you just have the system, the tube is almost a vacuum, and then what we observed, some current is running through, but there was a glow over there. These were first called the cathode rays. So this was the cathode. So this was a new phenomena for us. Now then first people thought that this was just some kind of an X-ray or a Röntgen. But what they had observed is if you put this system in a magnetic field or in an electric field, this glow shifted. So these rays, whatever they are, they were different than the X-rays that we had also observed more or less at the same times. So these were charged objects. And then eventually it was discovered that these are actually electrons. So if you create a large enough electric field, you rip electrons from the cathode, and they accelerate. Well, some of them will be cached by the anode, so they will close the circuit, but some of them just go through the holes and hit the other end, creating that glow. And, well, one way of measuring that, so here we have our system. Then what we do is we send them through such a system, and now we can determine how much they bend. So you have these, your cathode rays. Okay, let me just sketch from the book. This is the system where you have your cathode rays. Here you have a region where you put a large electric field, and you also create a magnetic field. Into the screen. This is your screen. So here you create your cathode rays. Then you send them through a hole. So here you create the electrons, you accelerate them, some of them will pass through. Those who go straight will pass through the hole, so you know that they are going in that direction. By changing this potential difference, you are essentially determined, by choosing this potential difference, you are choosing what the velocity of those electrons will be. So because if they cross a potential difference V, they acquire an energy of E cross V, that is their energy. So the energy of the electrons when they reach is E cross V. Now they reach here, they will bend depending on what kind of magnetic field you have. So on one hand we have due to the magnetic field, they will go over such a, if you create a magnetic field over there, their circular orbit, in this case there is no electric field, let's say over here. This will be the, this is the force they feel, this will be the central force, it should be mv squared over r. So this is essentially, so if we just simplify the v's, you get an E over m will be equal to mv over b. No, there is no m. V over br. So it's on one hand, you are determining B. R is something you measure. So how do you determine V? Well, you first create your system such that only these V's are selected. So you know what V is. So V is equal to E over B. So E over m is E over b squared r. So what you do, these are your cathode rays. In this region you have both E and B. So you just select only those particles who have a given speed. And then they enter this region. In this region there is no E, there is only B. So those particles will go around the circular orbit. So from that circular orbit you can determine what the radius is, what the radius of that orbit is. So you already know E. You have already chosen E. You know what B squared is. You measure R. So these things are, you determine them, devising your setup. The radius is what you measure. And that ratio gives you the charge over the mass ratio of whatever the particle is. And this is how we measured essentially the mass of the electron. Of course, this measurement doesn't tell us the mass, neither the energy of the electron, but it tells us what their ratio should be. And then there was the experiment by Millikan, oil drop experiment. Well, this told us what the charge of the electron is. So one experiment told us the charge of the electron. And now this experiment showed us the ratio of the electron charge to its mass. And if you just combine these two experiments, we discovered that the mass of the electron was something around 10 to the power minus 31 kilogram. Yeah, in fact, this is how you measure such masses, more or less. I mean, you cannot just weigh the electron and determine this mass. Any questions? Now let us discuss one more use of the magnetic field. So for example, this is where we use the electric and magnetic fields to determine the mass of some very small object, the electron. We can use the magnetic fields to study molecules or the contents of the molecules, the mass spectrometer. Well, the idea over here in the mass spectrometer is this one. Again, you have a very small hole where your atoms will enter. Here you have a magnetic field. Well, let's show it towards you. A uniform magnetic field. Now, suppose you have a material whose chemical decomposition you would like to determine. Well, you might not know determine the exact shape of the formula, but using a mass spectrometer, you can determine more or less which atoms exist. So what you do, you put your sample somewhere. You first ionize it. How you can ionize it? Well, mainly if you put it in a strong enough electric field, it will ionize. Then you have the ionized sample. Then you accelerate them through that hole. And then how do you accelerate them? Again, you can use electric fields. Now then they come here. And let's say if it's a positive charge moving with a velocity v, if it's a positive charge, what will be the direction of the velocity? Well, by applying an electric field, you are essentially ripping off electrons. So most of the ions will be positively charged. So what will be the direction of the force? Yeah, it will be downward. V is in that direction. Your palm in the direction of B. So the force is downwards. It will do a circular motion. So this will be its trajectory. Well, we had already determined the radius of this trajectory. No, not the radius, but we had determined the frequency. Oh, well, let's do it again. So we know that the mv squared over r being the radius of this trajectory, this should be the centripetal force, but that force is created by the magnetic field, QVB. Let's cancel the v's. So m, or is m over r in this case, QB over v. Well, depending on how you accelerate them, you will know the speeds of the object. So the radius, if the speed is, let's say, fixed, the radius is proportional to the mass. Did I do anything wrong? No. Okay. So if somehow you know that the speeds are the same, how can you know that the speeds are the same? Easy, use a speed selector. You can make sure that those atoms that reaches over here, they have the same speed. So v is known. Well, then the mass of the object will be basically given by this distance. The heavier objects will move a larger distance. The lighter objects will move a smaller distance. So this is the lighter. This is heavier. In fact, if you know V, if you know B, if you know the charge Q, which will most of the time will be probably 1, you can actually measure the mass itself by just measuring this radius. And in fact, this mass spectrometer is what led to the discovery of the isotopes. These isotopes are the same elements, but they just contain different number of neutrons. So their masses are different. So if you have the isotopes, if one of the atoms hit this point, its isotope will hit a very close by point, but not exactly the same point. It will go to a different point. And that way you can determine the differences, different isotopes of elements by using this mass spectrometer. And now let's go in another application, still another one. The idea is basically the same. If you have charges moving in a magnetic field, they bend. All of these are based on exactly the same idea. Now, up to this point, we have always said that no matter what are moving, the currents, we define the direction of the current as always the direction of the positive charges. If the electrons are moving in this direction, we said that the current is running in the opposite direction. That was the convention. And we said that it doesn't really make any difference. So negative charges moving in one direction is the same as positive charges moving in the opposite direction. Well, they are the same, except that in this effect. So here we will see that we can use the magnetic field to determine whether it is the positive charges moving around in a conductor or the negative charges moving in a conductor. Now, the idea of the whole effect is, let's just assume we have a conductor. This is our conductor. And we send the current through the conductor. And there is a magnetic field. Let's just assume the magnetic field is pointing into the screen. So this is our setup. Now let's say that this is just an ordinary metal. So the charge carriers are electrons. Now the electrons, since the current is running in that direction, what is the direction of the motion of the electrons on the average? The opposite direction. So the electrons are moving in this direction. What is the direction of the magnetic force acting on these electrons? Upward or downward? Down or up? What is the direction of V cross B? Let me see your right hands. Fingers in the direction of V. Rotate so that your palm points in the direction of B. Your thumb is the direction of V cross B. So what is the direction of the force? The charge of the electron is negative. The electron is fielding an upward force. So the electron will not just go straight. It will bend up. So this will be the trajectory of the electrons inside the conductor. Well, but this tells me that on the upper half, I will have an accumulation of negative charges. And on the lower half, well, there won't be so many electrons, so it will be positively charged. But now you see this creates an electric field in the vertical direction. The electric field will be pointing from plus to the minus sides. Well, what will be the direction of the electric force acting on this electron? It will be downward. You see, if you start the current, then as the electrons are moving in this direction, if there are no surface charges over here, they will bend up. So they will start accumulating on the top edge, and the lower edge will be positively charged. But this accumulation of charges at the top edge and the lower edge will create an electric field inside, and that electric field will exert a force on the electrons in the opposite direction. So eventually, the accumulation will be such that the speed of the electron is just E over, let me put that EH over B. And when the speed of let's say the drift speed of the electron, EH will increase until this is satisfied. Until this value, the electrons will keep moving up. Once this whole electric field is reached, the electrons will just go straight. One important thing is the upper edge is negatively charged, the lower edge is positively charged. Now let's consider another conductor. Let's say exactly the same setup. But this time, let's assume that the charge carriers are not electrons, but some positively charged objects. So the current is running in that direction. So positive charges are moving in this direction. What will be the direction of the force that these positive charges will be feeling? They will also, although they are positively charged, they will also feel an upward force. So as they are moving, their trajectory will bend up. Well, their trajectory will bend up. So the upper edge will be positively charged. And the lower edge will be left negative. And again, it will just keep going until EH will be V cross B, V times B. But you see, compare the two. If the charge carriers are negative, the upper edge will be charged negative. If the charge carriers are positive, the upper edge will be charged positive. So by looking at whether this edge is charged positive or negative, you can tell whether the charge carriers of your material is negative or positive. What will be the potential difference? Let's say this is D. The whole potential difference well, we know the electric field. It will be uniform. The thickness is D. So the whole potential difference is just VD times B. This is called the whole potential. Also keep in mind, this whole potential is not along the current. You see, the current is flowing in this direction. The whole potential is the potential difference between these 2 points. Perpendicular to, they are separated by a perpendicular distance to the current. That is what we call the whole potential. Any questions? Well, let's do an example. So this is question 69. So what we are given is basically a launcher. So that's essentially the system we had. You have parallel wires. A current is running through the wires. Now let me draw it properly. And then you have a movable rod on the wires, so that there will be a current running through the wires. The magnetic field is 1.8 Tesla and perpendicular to the plane of the circuit. The separation between these is 24 centimeters. The bar has a mass 1.5 grams. And what should be the current I? If the velocity initial is 0, the final velocity is 25 meters per second in a distance 1.0 meters. So basically we have this loop. This plate, very light, can move almost frictionlessly, and there is a magnetic field. So due to the magnetic field, it will feel a force. So if we want the force to be upward, what should be the direction of the magnetic field? Into the screen or out of the screen? Well, the force will be I. The force is I L cross B. L is in that direction. I want the force to be upward. So the magnetic field should be into the screen. So this is the direction of B. So how much force should we exert on this thing if we want it to go from rest to 25 meters per second in 1 meters? What should be the acceleration? Now this is the mechanics part. This question has nothing to do with magnetic fields, this part of the question. Well, the distance it covers in a time t is just at squared. And what else do we know? We know that the change in the velocity at the same time is just a times t. I want to find the acceleration, so I should somehow get rid of the t. I know delta x, I know delta v. I should get rid of the t between these two equations. Well, the t is just delta v over a. So this tells me that delta x should be 1 over 2a. T squared is delta v squared over a squared. So delta x should be equal to delta v squared over 2a. Or the acceleration that this rod should feel should be delta v squared over twice delta x. Well, we know how much speed change we are looking for. The speed change should be 25 meters per second. Divided by 2 times delta x is just 1 meters. Okay, I strongly advise you to keep the units whenever you are solving a question, to keep the units even in your mid steps. Quite often you just write the numbers, and at the end of the calculation, just add the unit. Well, let's see, what is 25 squared? 625 meters squared per second squared divided by 2 meters. So the acceleration we are looking for is 312.5 meters per second squared. So these one of them cancel. So at least I know that the units match. So this is not what I wrote afterwards, but this is what I derived from there. So it is the correct unit for acceleration. Now, what should be we know the acceleration. The mass is 1.5 grams. What should be the force acting on it? The magnitude of the force is mass times acceleration, 1.5 grams times 312.5 meters per second squared. So this is around 465 grams meters per second squared, which is 0.5, let's say 0.5 kilogram meters per second squared. So the force should be 0.5 newtons. So this is how much force the magnetic field should exert on our metal piece. Again, I repeat, this part at least is just mechanics, nothing with the magnetic field. Now comes the magnetic field. The force is I L cross B. Here the L is straight, B is uniform, so we can use that expression. The magnitude of that force is I, which we do not know. L, the length is 24 centimeters. And B is 1.8 Tesla. Sorry. That is the force. But we already know what should be the force. This should be equal to 0.5 newtons. Or the current should be 0.5 newtons divided by 0.24 meters times 1.8 Tesla. Well, let's see, this just gives us 2 around 1 ampere. Something like 1.2 amperes. This is how much current you need to have. And within 1 meter, this mass just goes from 0 to 25 meters per second squared. 25 meters per second. What is in terms of kilometers per hour? 25 meters per second. 25 times 3.6, something around 100 kilometers per hour in 1 meter. That's quite fast. Okay, any last questions? Okay, so I'll see you on Monday.